Thank you very much for your kind introduction and generous invitation. It's my greatest pleasure to give a talk on this matroids and matchings here in Waterloo. So the title of my talk is Unweighted linear metric parity algorithm, and some of you might have heard the same kind of talk of mine 5 years ago in the occasion of this Bill Cunningham's 65th birthday workshop. And to be honest, at that time, the result was mature. No, was prematured. And I was having very hard time writing the paper. And essentially, half and a couple of years ago, so I gave up writing the paper by myself and invited my younger colleague, Yusuke Kobayashi, to join this project. And Yusuke did an amazing job to reconstruct what I wanted to do. So now we have, a paper available online, and we presented the paper stock last week. Okay, so I would like to talk about that result here, but most of the time, or at least half of the time, I would like to spend some time. I would like to talk about the background of the problem, and then try to tell you some ideas of the work. Okay, and so since this is although this is a title of the paper, I think a little more, a little fancier title should be like this. Okay, and you'll see what it means in a couple of minutes, I hope. Okay, so let me start the story from Pfaffian. So given a skew symmetric matrix T, okay, and we want to construct a graph G of T in such a way that all these row sets, which is identical to the column set, should be considered as a vertex set. And each edge in this graph corresponds to the non-zero entry in the skew symmetric matrix. Okay? Now, the Pfaffian of the skew symmetric matrix T is defined to be the sum of the product, or actually, sum of the products of the non-zero entries, non-zero entries in all the perfect matching in this perfect graph. Oh, sorry, in this graph. Okay, and for example, this perfect matching corresponds to these three numbers, and it appears here as a product. And the sign for each matching is defined, in appropriate manner. Okay. So in some context of combinatorics, the way you define the sign here is important. But at least in this talk, the sign doesn't matter so much. Okay? The important thing is that the Pfaffian of the skew symmetric matrix, the square of this Pfaffian is equal to the determinant of T. That's well known. Okay? So one consequence of that is if we know that T is non-singular, okay, then there must be at least one non-zero term in this definition, in this expansion. And therefore, there must be at least one perfect matching in it. Now, does the converse hold? Well, actually, not always. It almost holds, but not always. It holds unless we have an unlucky numerical cancellations. But I want to say that the convex also holds in most cases, and in order to make this formal, I would assume that suppose that each non-zero entries in the skew symmetric matrix is indeterminate. Then we could argue that, the T is non-singular if and only if there exists a perfect matching in G of T. Okay? Now, such a matrix, I mean the skew symmetric matrix with non-zero entries being indeterminate, is named the TAT matrix by Jim Gillen. Okay? And the name came after this famous paper of Bell-Tutt, okay? The factorization of linear graphs. So this paper is famous because it gave the first characterization of when the graph has a perfect matching. Okay? So it said that the graph has a perfect matching if and only if for any vertex set X, okay, removing X from G, from your graph G, will produce, say, odd components, odd connected components of odd cardinality of vertices, say no more than the cardinality of the set you deleted. Okay? Now, this is a very good example of what is called the good characterization later by Jack Edmonds. Now, I have a potentially embarrassing question to you. How many of you actually read this paper? Please raise your hand. Oh, okay. Good. Well, actually, so what I want to say is that, so the name of this Tutte metric came after this paper because in order to prove this theorem, Tutte actually used that characterization, that matrix, okay? And the argument there is in fact some algebraic, say, manipulation of the Pfaffian, okay? Now, but since later, there have been, say, established some more, say, elementary or combinatorial proof for that. And many textbooks, adapted that. So it's not so surprising that many of you haven't read it, okay? And I must confess that I read it only a week ago. Okay. But the main message here is that, say, the Pfaffian, the concept of Pfaffian is a very powerful and useful tool, not only for the matching, but also for its matroidal generalization. That's the main topic of my talk, okay? Now, not right after, but after this, say, characterization, this was extended to a characterization of the number of maximum, maximum size of the matching, and which is now called the Tutte-Belge formula. And once this formula was done, and the question is, how can we find the maximum matching, okay, efficiently? And that was done by Jack Edmonds, under the name of the augmenting, who developed the augmenting path algorithm using this blossom technique. So blossom is a very key concept in his algorithm. And in the paper of Edmonds published in the same year, in another paper published in the same year, he has also, investigated the maximum weight matching problem, okay? And this paper actually introduces a way of, say, some polyhedral combinatorics. Say, developing a beautiful algorithm based on the polyhedral combinatorics, okay? Now, so this is a very beautiful world, and another beautiful world in this combinatorial optimization is the so-called, say, Matroid intersection. So suppose you're given a two Matroid that shares ground set in common, okay? So here, and what we want to do is to find the maximum size common independent set of the two Matroids, okay? And the maximum size is, in fact, characterized by the minimum of the rank of the one side and the rank of the other Matroid, okay, of the complement. And again, for this problem, so augmenting path algorithm was developed by Jack Edmonds, and also the weighted Matroid intersection was solved by a sequence of papers in the 70s, okay. Now, these two problems are both generalization of the bipartite matching. But not only that, they also, share some common features, like the polyhedron of the convex hull of the instance vectors of the feasible solution forms can be described by exponential number of inequalities. Still, you could exploit the primordial connection to develop our efficient algorithm to solve the problem, okay? So this is a very beautiful world, and so therefore, it's quite natural to think that if we could want to have a common generalization of these two frameworks, okay? So in the 70s, there are actually a few such frameworks were proposed, and under the name of Matroid parity, Matroid, or Matroid matchings. And they turned out to be equivalent to each other. So in this talk, I will mainly focus on the framework of Matroid parity due to the simplicity of its presentation. Okay? Now, if we could solve all of these, if we could solve this efficiently, then we could have understand, say, all these beautiful world under one umbrella. But actually, the life was not so easy, and also interesting, even more. Okay. So let me try to formalize what the matroid parity problem is. So suppose you have one matroid, okay, on the ground set V, okay, and your ground set V is partitioned into pairs, okay, which is called lines. Now, a subset of the ground set is called a parity set if it is a union of lines. So what we want to do is to find an independent parity set of maximum size. Okay. Now, is the problem clear to you? Now, I want to briefly mention how this extends the previous two frameworks. So first, let me talk about this matching. So you have a graph, okay? If you have a graph and think of this edge set. Now, we say we will consider the set of the half edges, okay? That means that you divide all these edges into two parts, okay? And we consider the partition matroid on the set of half edges. So that the partition is defined by, essentially, the independent set must contain at most one half edges that is, say, incident to each vector. Okay. Now, this way, but in order to get the parity set, you have, if you choose this one, then you have to choose that one. Okay. So this way, the independent parity set corresponds to a matching in this framework. Now, let me talk about the matroid intersection. Suppose you have two matroids M1 and M2 on the same ground set E. Now, we make a copy E1 and E2 of E, okay? And consider the matroid on this side and another matroid on that side. And now we consider the direct sum of these two matroids of the entire matroid on that ground set, okay? Now, if you choose that one, I want to choose that one as well. So this corresponds to the same original elements, and then gives you, say, lines in this your, say, larger matroid. So the matroid parity problem in this setting corresponds to the matroid intersection problem. Okay. Now, so can we solve this matroid parity problem? Well, actually, it turned out that this problem is intractable in a general setting. When I say general matroids, I mean that we assume that the matroid is given, say, by this independence test oracle. Okay? In this setting, it was proved by Lovers and independently by Jensen and Kolte that actually we have to call independence oracle exponentially many times to get this solution. So this intractable result is independent of the assumption like NP is equal to P. Okay? And some more recently, Lee, Sviridenko, and Fondrak developed the so-called PTAS, the polynomial time approximation scheme for this framework. Okay. Now, but that's not the end of the story, and what is more surprising is that, say, when we consider the linear matroids, now we have this min-max theorem that was shown by Lovers, and so actually he first gave this min-max theorem and say, turn the argument into a polynomial time algorithm. And since then, there have been, say, developed a number of more efficient algorithms. And here, the R corresponds to the rank of the matroids, and M corresponds to the cardinality of the ground set. Okay? And the fastest deterministic algorithm is of the order of the, say, R cube M. Okay? And this one, so Lapchi-Lau and his former students developed an even faster algorithm, which is based on the randomized algorithm. Okay? Now, so this is the state of the art for this the unweighted linear matroid parity problem. So let me tell you how we can solve this linear matroid parity problem to some detail, so that you can, so that we could have an idea of how to solve the weighted version as well. Okay, so So linear matrix party, when we say that a matroid is linear, it means that this, say, the matrix corresponds to a linear independence of the column vectors of your, say, matrix. Now we are given a matrix A, and we say that the column set is V and the row set is U. And basically the V is the column set is our ground set of the matroid. And we assume that so this, say, ground set is partitioned into pairs. Now, we want to find an independent party set of maximum size in it. And we denote by nu of A the maximum size of the independent sets, and mu of A to be the, say, maximum number of line in a base. Okay. So the Lopez min-max theorem is so written like this. So the maximum number of the say lines, independent lines in it is equal to the minimum of this. In the right-hand side, say the minimum is taken over all linear subspaces in the span of A. And basically, after, say, taking the quotient by this K, we think the rank of this, say, rank of the span spanned by some partition, each component of the partition, and round it down by, say, divided by 2 and round it down and take the sum. Okay? So it's not too difficult to see that the right-hand side is at most, right-hand side is no less than the left-hand side. Where he has proved that this holds, and so is this really useful? And actually, linear matrix parity has, say, surprisingly wide variety of applications. So coming from this electric network circuit, electric network analysis, and combinatorial rigidity, or graph embedding, or the disjoint process. And so based on this fact, we want to have, as a first algorithm, to solve this linear matrix parity problem. And so I will explain one algorithm, okay, and which is very connected to the weighted version. So the starting point is a skew symmetric matrix formulation of the linear matrix parity problem, which we, say, somehow introduced with my joint paper by Jim Gillen. So here is a matrix A that is given. And we consider the minus F transpose. And we take these two, say, we attach these 2 by 2, say, diagonal, block diagonal matrix with 2 by 2, having 2 by 2, say, skew symmetric matrix, where the off diagonal is supposed to be indeterminate. So this 2 by 2 matrix corresponds to the partition into pairs, I mean the lines. Okay. Now, we have shown that, and actually it's not so difficult to see, that the maximum size of an independent party set in this problem is equal to the rank of this skew symmetric matrix minus the cardinality of the ground set. Okay? So, so please keep this formulation in your mind for a moment. And I will try to tell you the algorithm how to find the optimal solution. Okay? Now, suppose we have a base, B. And if we have a base, then I want to check if we can improve this base. I mean, if we have a base, then automatically we have this base determine the, say, independent party set included in it, the largest independent party set included in it. Okay? And the question is if we can change the base so that we could improve the number of this independent party set. Okay? Now, in order to do so, we consider this auxiliary graph. Okay? So given a base, we can actually transform this submatrix to the unit matrix, okay, by some row transformations. And then we'll obtain this say, matrix of the right-hand side. I mean, so indexed by the non-base part. And this is often called the fundamental circuit matrix. Okay? And non-zero entries in this fundamental circuit matrix corresponds to the pair of U and V, so that we can make a single exchange, U and V, to obtain a new base in this matrix. Okay? So if we have this circuit matrix and we consider this edge set F, so that gives you the exchangeability of the value of vertex sets. And also, we also have this edge set L, okay, which corresponds to the line, set of the lines. So whenever we draw this kind of pictures, I mean that the blue dot corresponds to the vertex in the base, and white dot corresponds to the basic, say, in the say, complement of the base. Okay? And this green edge corresponds to the exchangeability arc, defined by that way. And this blue edges corresponds to the line, corresponds to the pair of the, say, vertices. So exchange as green edges is from blue one to white one always. Okay? But blue one may connect to this, say, both blue one or both white one, or it could have white and blue. Okay? So, and this kind of line will be called the source line. Okay? If we don't have that one, that means that our base is already a parity set. So that must be the maximum one. Okay? So what we want to do is to reduce the number of source lines. And how can we do that? Okay? So this is a basic idea. Suppose we have this kind of, say, configurations in this auxiliary graph. And here's a source line and source line. So we want to find a path between source lines. I mean, from one vertex in a source line to another vertex in another source line that uses green and blue alternatively. Okay? And such that if we change the base along this path, it will produce a new base. Okay? To obtain that, and if we try to find this, say, such a path by breadth first search, and suppose we can find that one, then to do so, for example, you will start from here and find an adjacent vertex by green edge. Okay? And then we can immediately move by a blue one. Okay? And then we can start from that one to that one. So if that is the case, then we could still have some kind of green edges adjacent to this blue vertex. Okay? That may remain. But if we have arranged these green edges in appropriate order, we will see that this bipartite graph has a special property, that it has only, it can be, say, ordered appropriately, so that it corresponds to the upper triangular form of the matrix. Okay? And if we have an upper triangular matrix with non-zero diagonal, then that must be non-singular. So such a submatrix corresponds to the fact that if you take the symmetric difference of B and this, say, augmenting path, you will obtain a new base. So this phenomena already, say, appeared in the augmenting path algorithm for Matroid intersection. And the essence of that algorithm is already actually this, say, the fact that the triangular matrix must be non-singular. Okay? Although you have to work a lot to prove that in a combinatorial context. Okay? Well, coming back to this linear metric parity problem, so we are happy if we could find this kind of path, say, by breadth first search. But metric parity problem is not so easy. So we could find this kind of configuration. So when you apply this breadth first search from that point, we do not go into this branch. But if you find this kind of, what is this? 9gon. 9gon should be, okay, no, never mind. Is it 9? 11, yes, even more. Okay. If you have this kind of configurations, then we know that we could actually come this way to go this branch. Okay? If we have this kind of thing, then actually this should be recognized as a blossom. Okay? Now, if we have a blossom, what do we do? We want to shrink it, yeah? But we have to be careful. If we shrink it, that means that any edges that goes out of the blossom should be useful for our search, okay? So this seems to be okay. But when it comes to that case, we could have go this way, okay? But we also could have go this way. And two moves can cancel each other if we think of the 2 by 2 symmetrics here and the determinant is equal to 0. Then we shouldn't go to that direction either, okay? So this means that the graph structure cannot tell you everything. We still have to refer to some numerical information, okay? Now, what should we do in that case? And what we will do is actually like this. So if we find this kind of blossom, we introduce a new vertex called tip, okay? And it's made T over. So T is defined so that it is, say, at least in the outside of the blossom, it is a copy of this S, one of these, say, adjacent to this bud. And this T bar is simply defined so that it is, say, it has 1 to this corresponding to T and has 0 otherwise. Now, if we have this, and then we can apply some transformation that, say, try to delete this part by this part, okay? By these column operations, we'll obtain that, okay? Now, as a result, and we can also delete this as a 0. So as a result, if the original determinant is equal to 0, this point should be 0. Otherwise, this should be non-zero, okay? That corresponds to the path like this one. Sorry. That corresponds, okay. So by doing that, we must have this edge. But important thing is that, say, if this is non-zero, we have this edge between U and V. If we have this U and V, that means that we could have route that way to go here, okay? If not, we don't continue the search. So this is a basic, say, ingredient of the augmenting path algorithm. And so if we find an augmenting path, then we will exchange. We will make say, augmentation. And forget about blossoms and start from scratch to find an augmenting path. If we find, then we continue. Continue. At some point, we should get stuck, okay? What if we can't find our augmenting path by searching that way? So here's a very important philosophy behind augmenting path. So if you get stuck, you must be able to find something good, okay? So, in fact, if you don't have any, if you don't find, say, augmenting path, then you will obtain this kind of configuration. So look at here. So we have this, say, source lines, and we have started these, say, searches. And the thick lines corresponds to the edge that we used in the search. And the thin lines corresponds to the edge that may exist but didn't use in the search, okay? Now, if you look at that, then we will observe that each these orange component that corresponds to the, say, either blossom or line or the area that we didn't search at all, okay, that we didn't reach in the search, okay? Now, in these, say, blossoms and lines, we have at most one vertex, okay, that is connected to the that is incident to the edge that goes outside, okay. We didn't have the other ones because, okay, so I should say that just saying that is if you have these edges, at least one of its endpoints should be, say, marked by red, okay? we can find this red part. So this in the blossom, the red part corresponds to the tip, and in the line, the red part corresponds to the vertex, which is closer to the source. Okay. Now, if we have that, so what can we do? Let me go back to this matrix formulation. So what we want to do is to say that our current base is in fact an optimal solution. Now, remember that we started with this skew symmetric matrix, but if we apply this algorithm, we have added some, say, tips and the mates of tips, okay? That corresponds to this, okay? This T part. Now, so we basically, our algorithm are looking at this part. So let's look at that. But before, I should say that when we add this, actually the rank of this matrix is increased by just the cardinality, exactly the cardinality of T. Okay? So our optimal value is characterized by the rank of that one as well, okay, this way. Now, so if you look at that part, we'll see that, say, all these points are partitioned into components, and in each component you have at most one column or row that contains some off diagonals. Other parts are all zero. Okay? If we have that, we can simply add one column, say, corresponding to this column, we can simply add this one row, having this one here as a non-zero, and other places to be zero. Okay? And the same for this. For the row, we could have this column, add some column, and put one here. Okay? And using these vectors, we could actually apply column transformation so that all these non-zero parts should be vanished. Okay? Now, we can apply some permutations of rows and columns so that we have this block diagonal form at the end. Okay. Now, so come back to the skew symmetric matrix. What does this imply? So we have added this Z part, okay, corresponding to this new additional columns or row to this skew symmetric matrix. And if we apply appropriate permutations of the rows and columns, then we obtain this part. Now, except for the part that is not reached by the search, all these components actually become the odd size skew symmetric matrix. Why is this so? So basically, we have two types of components. One is a component that contains source lines, and the other one is the component that doesn't contain source lines. Okay, let's start with a component that doesn't contain source line. If it doesn't contain source line, we have added, say, tip and mate of tip. In addition, we have added this Z, okay, new additional one. So that would make that would make it odd cardinality. When it comes to the source line, the one that contains source line, so it also has it seems to have a, say, even number of vertices. However, the vertex in this base is double counted, and the vertex in this non-base is single counted. And so if you have a source, say, source line, so that will give you the odd size skew symmetric block of this here. Okay? So in either case, we have that. Now, but as I told you before, or maybe I forgot to tell you, that say skew symmetric matrix of odd size is singular. Okay? So we can evaluate the rank of this skew symmetric matrix, which must be equal to the rank of that one. Now, I can tell you that the rank of this skew symmetric matrix must be at most the size of this matrix minus the number of, say, odd diagonal blocks. And in fact, if we pay attention to Z minus this say, terms, then it is equal to the number of the source lines. what does this mean? So we have already seen that our optimal value is given by this way. And since adding the rows and columns doesn't decrease your rank, so we have this inequality here. Now, this is it, okay? And if we apply that inequality to this, and we obtain that your say, optimal value is at most the cardinality of u, which is equal to the rank, minus the number of the source lines, okay? Which means that this is, in fact, the size of the parity set induced by your current base, which means that we already have some solution which is at least good as an optimal solution, which means we are done, okay? Now, so actually this algorithm is not really new, not really old, okay? It just comes from this, say, specialization of our weighted algorithm to this unweighted case, okay? But one can see this as a modification of the augmenting path algorithm by Gabor and Stallman, and this optimality proof technique actually was inspired by my joint work with Jim Gieden and Kazuo Murata on the delta metric parity problem. Okay. Now, so let me talk about this weighted linear metric parity problem. And so, coming back to this problem, okay, so we have a matrix A, that each column is partitioned into pairs, and in addition to that, we suppose that, say, all lines have its own weight. Okay, each line has its own weight. And the weight of a base B is just a sum of this weight of the line in it. Okay? Now we want to find a parity base. Parity base means that the base that is simultaneously, that is also a parity set. Okay? Now find a parity base of minimum weight of that. So this generalizes the minimum weight perfect matching problem in general graphs, and also that generalizes the minimum weight common base problem of two linear matrices. Okay? And as a weighted version of the linear metric parity problem, one can think of finding, say, maximum weight independent parity set. Okay? And these two problems are actually equivalent. So I will talk about this setting. Okay? And what's known about the weighted linear metric parity problem? Actually, so was not so many results were known before. So there was at the beginning of the 90s, there was say, randomized pseudo-polynomial algorithms by Camerini, Galviati, and Maffioli. And say Laptiao and his former students made this faster using some techniques. Okay? But still, it was randomized pseudo-polynomial algorithms. An application that includes, for example, the approximation algorithm for Steiner tree. And so the Prommel and Steger gave 5 third approximation algorithms for that. So at that time, there was a very good approximation ratio. But nowadays, for example, this Laura Saniter and her co-authors developed a much better, strong, say, approximation ratio. Okay. So, but I still hope that there should be a way to exploit this, say, weighted linear metric parity problem as a tool for this design of approximation algorithms. And also, a recent paper of Yamaguchi showed that, say, weighted version of this disjoint S-plus problem can be solved exactly by this weighted linear metric parity problem. Now, okay, so here is the main result and tools. So we have developed a combinatorial deterministic polynomial algorithm that requires order of Rn cube arithmetic operations. Okay? And so the main tool here is a polynomial matrix formulation, just like before, but as a polynomial version. And there's some idea comes from the combinatorial relaxation of Kazuo Murata, which I will not talk into some details. And also, it is based on this augmenting plus algorithm, Gabor-Stallman. Okay. So what is a polynomial matrix formulation? So here is a polynomial matrix, skew symmetric polynomial matrix in theta. Okay. So this is quite the same as before, but in these diagonal blocks, we have this indeterminate alpha L times the theta to the weight. Okay. Here in the exponent of theta, we have the weight of each lines. Now, and we can easily prove that actually the minimum weight of a parity base is equal to the sum of all this weight minus the degree of the Pfaffian of this skew symmetric matrix. Okay. Now, since this is a polynomial matrix in theta, Pfaffian should become this polynomial, and its degree takes this largest, this largest exponent in this expansion. Okay. Now, and in this algorithm, we use the same kind of, say, concept called blossoms. But if you consider like a, say, blossom algorithm for minimum weight perfect matchings. So there, after augmentation, you have to keep the blossoms as it is. Whereas in the unweighted case, you can, say, expand it after each augmentation. So here we have the same kind of difficulty. So but I will, tell you this difficulty later a little bit. Okay, so here the blossoms are the, say, laminar family, and that is basically consists of some, say, lines and some additional new vertices. Okay, and we have two types of blossoms. One is a normal blossom that doesn't contain source lines. In that case, just like before, we add some, say, new tip and its tip mate. Okay? And if you have a source blossom, if it contains a source line, it is called a source blossom, and you don't have to add some tips and so on. Okay. Now, and given that kind of laminar family, we introduce a kind of dual variables. Okay, so here I have to remark that I don't introduce LP formulation of the problem explicitly. Okay, so the term dual just means that we can use this kind of variables as just a certificate for the optimality, and we want to keep it. Okay, now to be more precise, we have these two kinds of variables. So first variable P is attached to each vertex. And the second, and which takes any, say, real numbers. And another variable Q is, say, attached to the, attaching some non-negative values to each blossom. Okay? And given this, say, a laminar family and these dual variables, for any, say, pair of U and V, we can introduce a quantity called Q of U, V, which is basically the sum of this, say, sum of the blossom variable among all these blossom that crosses U and V. However, if U or V is used as a tip of a blossom, okay, then we will negate that part. We will take minus that part. That's somehow a bit non-trivial trick. Anyway, and based on that, we introduce this dual feasibility like this. Okay, so the first condition is that your dual potential P and P, PU and PU bar. U bar means the mate of U. Okay, U and U bar corresponds to the line. And so the sum is exactly is a weight. So this gives you a weight splitting. Okay. Now, and for any, say, pair that appears in the auxiliary graph, then we must satisfy this inequality. Okay. And at the end, this, say, potential for the tip and the tip mate must be equal. Okay. Now. So can we actually find this kind of potentials? Well, for example, to start with, we will start from this, say, we'll start the algorithm as an initialization that the lambda is empty. So if lambda is empty, we don't have to worry about that, and we don't have to worry about this. Yes, we don't have to worry about that as well. So that means that you have, say, exchange arc between u and v, then P of u must be larger than P of u. P of v must be larger, is equal to or larger than P of u. Okay? That corresponds to the situation that B minimizes of this, say, the sum of the potentials of your vertices, okay, among all bases. So to start with, we actually find an arbitrary rate splitting that satisfies the first condition, and then find a base that minimizes, okay, the sum of the base. Now, this is the outline of our whole algorithm. So we start with this initial feasible solution that satisfies this dual feasibility, okay? Now we have a base. Now, is this a parity base? If it is, then we have obtained a solution, okay? If it is, since it is it attains the minimum base among all, and if it is parity set, then that's done. Okay? If not, suppose not, then the math have some source lines. So we want to find an augmenting path from the one source line to another source line. Okay? And in a very similar way in the unweighted version that I explained before. Okay? The essential difference here is that we use only the tight edges. That means the inequality, the second, say, feasibility condition must be sharp. Okay? So we use only these kind of edges as the green edges to find an augmenting path. Now, if we find an augmenting path, then we can make an augmentation. And if we don't, then here's again our, say, idea that if you get stuck, then you must be able to improve the dual side. Okay? So if you don't find an say, augmenting path, then you will update the dual variables. Okay? And I will tell you how to apply this, say, dual variables, but we will design the algorithm so that there will be a new tight edge in it. And we come back to this again. Also, we could prove that if this will not give you a new tight edge, then the problem itself is not feasible. It's not feasible. That means that you didn't have a parity base. Now, so let me tell you how to update. So basically, for each blossom, or I should say that for each maximal blossom that achieved in this way, I mean through the tips, and then you must increase by some positive amount. You must increase their variable for this blossom. And if you achieve the blossom in this way, you must decrease the value of this epsilon by epsilon. So all the dual variables that changes must be connected to the maximal blossom or these, say, vertex outside the blossoms. Okay? So that is quite the same the standard algorithm for the minimum weight perfect matching. Okay? Now, and in fact, we'll be able to see that these changes will not hurt this, at least for if the epsilon is sufficiently small. Now, and we'll be able to find that the maximum amount of epsilon that will keep this dual feasibility. And if you attain that, then we fix this epsilon and apply this update. So that means that we will have, say, tight edge somewhere. Okay? And we'll repeat that. So as a whole, searching for an augmenting path requires the n square operations, arithmetic operations. And these updates can, say, iterate, but at most order of the n times. And also this augmentation requires, this only, say, the number of, the rank. The number of iterations should be at most rank. So we'll obtain this all n cube algorithm. Okay. Now, the first thing, okay, And technically, the most difficult part is after this augmentation, I have to certify, I have to say, make a guarantee that this augmentation keeps these dual variables feasible. Okay? Because this augmentation changes the basis, so it will change this auxiliary graphs, say, drastically. And still we have to, we have to be able to prove the feasibility. Okay. Now I want to tell you this. So at the end of the algorithm, we obtain this parity base and the dual variables. And I want to tell you the idea of the optimality, of the proof of the optimality. So again, let me remind you that we have this skew symmetric matrix. And taking this base, we have this, change it. We have applied these raw transformations and apply these, say, permutations to obtain that, okay? Now, so we want to know the degree of the Pfaffian of this matrix, but what we have done in the algorithm is that we have just added these tips and tip mates, okay? But the way we added that actually corresponds, say, for each non-zero entries here, so actually this part should be, should be like a unit matrix. And for each non-zero entry here, either the rows or columns must be 0. Okay? So that means that if you think of the Pfaffian of that one, and it is exactly the same as the one before. Okay? Yes. Or I should say at least the degree is the same. Okay? Now, so we made these, say, transformations in this size, but that also doesn't change the Pfaffian. Okay? And so here we have this Pfaffian, and skew symmetric matrix in hand, and now consider the graph G of that one. Okay? Consider there's a graph that corresponds to the zero non-zero pattern of this matrix. Now, here we have U that corresponds to that part, and B, and say B, the complement of B. Okay? So this is just parallel because it corresponds to this identity matrix, and this part corresponds to this T that is added in the algorithm. Now, look at this and attach each edge the weight 0. Each green edge, we attach the weight to be 0. And for the edges coming from the lines, we have the, say, original weight. Now, we want to evaluate the, say, Pfaffian, the degree of the Pfaffian of the skew symmetric matrix. So what we should do is to consider the maximum weight matching in this graph. Okay? This weight comes from this, say, the degree of this matrix. Therefore, it's quite natural here. And to do that, and we might have our, say, unlucky numerical cancellations. So this, say, maximum weight perfect matching gives you just the upper bound of the degree of that side. Now, to give, I'll say, to bound this upper, to understand this upper bound, we should consider the dual linear program of this maximum weight matching, maximum weight perfect matching problem. And this is so written like this. So here we have this, say, dual variables attached to vertex and also the Bloxham variables. Okay? And we know that this maximum weight of the perfect matching is at most a dual objective value. The dual objective value is given like this. So what we want to do is that we already know that we have a base and we have some dual variables, which is P and Q. And we want to construct a dual feasible solution of this problem from dual variables P and Q, okay, that we obtain in the algorithm. Okay? And we have an explicit definition of that here. The important thing that we can, say, define that, okay, in a consistent manner. And in particular, coming from this Bloxham, we throw this tip away and to obtain this odd vertex sets. Okay, so and then concerning this odd vertex, we give this Blossom variables here, but we also say add the same to this vertex tip. Okay, so that if you consider the dual objective values, this contribution of Q will disappear. I mean, it cancel out. And also, if we take this, say, some of these variables, we'll see that actually, so for each these pairs, we have this P and minus P, so they are canceled out somehow. Okay, so what remains is the sum of this P in the right-hand side. So that means here. So we know that the maximum weight of the perfect matching gives the upper bound of the degree, but this is at most the dual objective value, which is equal to that one. Okay, and this, because this gives us say weight splitting, we know that this corresponds to the sum of the weight in the co-base. Okay, in the complement of the parity base we have, but recall that our optimal solution, optimal value is given like this. Okay, if we combine this together, we obtain that one. That means that hey, this is the optimal value that we had in mind, but this is in the right-hand side is a way that we actually have. So that means that what we have is at least as good as the optimal one, which means we are done. Okay. So here's the conclusion. So we have developed an algorithm that finds a minimum weight parity base with these arithmetic operations. And actually, for linear Matroid that are represented over a fixed finite field, this runs in this complexity. Okay? But if we have a linear Matroid represented over Q, then we have a kind of issue, so that concerning the size of the bit, concerning the size of the number that we have to deal with. And so right now we don't have a good bound, so therefore we can't claim that we have a strongly polynomial algorithm for this case. Okay, however, we can have a trick. We actually have a trick to solve this problem in polynomial time. Basically solving say a polynomial number of weighted linear metric parity problem over the finite field. Over say some quite a number of over some primes. And the number of primes that we have to test can be bounded somehow, using some relations between them, say, the distribution of the prime numbers and so on. So that sounds cool. I don't know, actually. But I don't find it quite satisfactory anyway. So the question remained, so what is actually a polyhedral description of that? So one good aspect of our approach is that we could solve the problem without knowing the polyhedral description. Okay? That's one thing that I'm proud of. But on the other hand, once we have an algorithm, we should be able to find this polyhedral description. Okay? And the issue that I mentioned before, the space complexity over Q, and we should be able to make a first implementation or the first algorithm that is completely different from that. And since we now have an efficient algorithm, it's a good time to find more actively the application of this problem. And so I didn't tell you at the beginning, but actually the Matroid matching theory of Lavois was more powerful than this linear Matroid is applicable to more, as I say, wider class of Matroids than linear Matroids. And we don't know how to extend the story, the theory, to this weighted version of that class. So that includes, for example, the algebraic matrices and so on. So you're all welcome to join us to see the mystery of the Matroid matching. Thank you very much for your attention.
So I'm a little naive about all the details here, but you're using the P and Q as dual variables in quotation marks, and I was wondering if the polyhedral description, I mean, it seems to me it would naturally come from a better understanding of those variables, right?
Yeah, that's what, I'm dreaming of, yeah.
So you have the this box where you've got the augmenting path algorithm as part of the approach. But could you do that with if you just had some black box implementation of Matroid matching, unweighted Matroid matching?
Yeah, that would make this description much easier. Yes, but well, right now I don't have. Right, that's one thing that I can hope. Yes.
And the second question is, what about delta matroids?
So how many of you know delta matroids? Good, it's becoming popular. I'm very happy to stay in the delta matroid hotel in Waterloo. So I think it is, so the idea comes from the skew symmetric matrix. So it is very plausible that we can extend it to the delta matroid. But still, there should be some kind of, say, a technical difficulty there, but which can be overcome, I think. Okay, thank you.
Are there any more questions?
This is getting at the faster implementation question that you have. So you're spending n squared time to find an augmenting path, and you have O of n phases. Do you think it's possible to get the phases to maybe O of root n or something like that, like the Blossom algorithm, or the fastest implementation of the Blossom algorithm?
Oh, good questions. So maybe not.
Your goal was correctness, so I think going for that root n would only make it more complicated. So.
But even for the non-bipartite matching, it's very complicated.
Yeah, it is.
Yeah,
it is.
it is.
But at least there's proofs now.
Yeah.
It's correctness.
Good.
Supposedly.
Yeah, thanks.
Yeah.
Yeah, let's be positive.
Yeah.
Are there any more questions? Okay, if not, I'll mention, oh, sorry, was there a question? No. If not, I'll mention there's, as always, a reception across the hall right now, and I'll ask you to join me in thanking our speaker again.